Let's just face it, we are absolutely drowning in data. But what happens when that data is just a giant, messy, unorganized pile? No labels, no tags, no instructions on what to do with it. How on earth do we find the hidden story inside all that noise? Well, that brings us to a really fundamental question.
And that's the big puzzle, isn't it? It's kind of like someone dumping 1,000 jigsaw puzzle pieces on your table. But here's the catch. They're from 10 different boxes, all mixed together, and you've never, ever seen the pictures on the box lids. You have to find the patterns completely on your own.
So to really wrap our heads around this, let's use a brilliant little thought experiment. Imagine an alien lands on Earth. It wanders into a library. It can't read our language, so the titles, the genres, the author names, they all mean nothing. To the alien, the data is completely unlabeled. But it's a very tidy alien, and it's determined to organize this chaos.
So what's the first thing our alien does? Well, it uses its eyes. It sees that some books are huge, thick, with hard covers, while others are really thin, kind of floppy, and they're full of colorful pictures. So it just starts making piles. All the thick books go over here, and all the comic books go over there. It's creating groups based on features it can actually see. Next up, the alien has this little aha moment. It realizes trying to understand every single page of every book is just impossible. But it starts to notice a pattern. Books with spaceships on the cover seem to belong together, and books with dragons on the cover, they belong in another pile. It's found a shortcut. A single feature, the cover art, can stand in for the whole complex book. It's simplifying the problem.
And finally, this is where it gets really clever. Our alien starts watching the humans, and it spots a hidden rule. Every single time someone checks out a book from the pile with all the weird math symbols, they almost always grab one from the pile with the diagrams of falling apples. It has just discovered a deep connection, a hidden relationship between two groups that seem totally separate.
And just like that, our brilliant alien, with absolutely no instructions, no teacher, and no ability to read our language, has just perfectly demonstrated the 3 core ideas behind unsupervised learning. It's a way for machines to learn without a teacher.
So what makes this so different from the AI we usually hear about? This slide just nails it. Supervised learning is when you already have the answers. You show a machine a picture of a cat and you tell it, hey, this is a cat. But with unsupervised learning, you just give it a massive folder with 1,000 animal photos and say, go figure it out, organize these. The machine, all on its own, might come up with groups for fluffy things or things with wings or long-necked things.
And that brings us to the formal definition. At its absolute heart, unsupervised learning is all about algorithms that just dive headfirst into raw, unlabeled data to discover the secret architecture hidden inside. It's all about exploration, not instruction.
Now, let's look at this table because the difference is really key. Check out the goal row. Supervised learning, with its labeled data, its whole purpose is to predict the future. Unsupervised learning, on the other hand, uses unlabeled data to understand the present by finding those hidden patterns. So one predicts, the other discovers.
Okay, so let's break down that alien's strategy into the 3 key tools it used. First up, remember that very first action, making piles of similar-looking books? Well, in machine learning, we've got a name for that. It's called clustering.
The whole point here is really simple. Find the natural clumps in your data. The algorithm's job is to put data points together based on how similar they are, or you could say how close they are to one another, and in doing so, it creates these distinct clusters. But how does a computer actually do that? Well, a really popular method is called k-means. It's pretty cool. You just tell it how many clusters you're looking for, let's say 3. It then plops 3 random center points into your data. Then it assigns every single data point to whichever center is closest. And then it finds the new middle of those groups and moves the centers. It just keeps doing this little dance over and over until the groups stop changing. It's simple, but man, is it powerful. And this is where you see the real-world value. A bank can feed in data from 1 million customers, things like income, age, spending habits, and a clustering algorithm can just find these natural groups. The bank didn't go in and label anyone. The algorithm discovered the structure all on its own, creating segments like high spenders, savers, and maybe risky borrowers. Okay, on to our second tool. This one ties right back to our alien's second move, simplifying a whole complex book down to just its cover art. This technique is called dimensionality reduction. Sometimes your data just has way too many details, too many features. It's noisy, it's messy, it's hard to work with. This technique basically acts like noise-canceling headphones for your data.
It reduces the number of variables, boiling everything down to just its most essential, most important components.
A perfect example of this is image compression. You actually use this every single day. When you send a photo to a friend, you're not actually sending every single one of the millions of pixels. An algorithm reduces the data, but it keeps the most important features, the lines of a face, the color of a shirt. So the image is still totally recognizable, but it's way, way smaller and faster to send.
And that brings us to our third and final tool, which mirrors our alien's ultimate discovery, that hidden link between the physics books and the calculus books. This is what we call association rule learning.
At its core, this tool is basically an if-this, then-that finder. Its whole job is to sift through mountains of data to discover those interesting, often surprising relationships between things. It finds the hidden rules of the road. And this quote right here, this is the granddaddy of all association rules. It's from something called market basket analysis. Supermarkets use these rules to figure out which products are almost always bought together. That's why the beer is sometimes next to the diapers. It allows them to totally optimize store layouts and promotions. Now, I know alien librarians and grocery carts are fun, but you might be thinking, how does any of this actually affect me? Well, the truth is, these tools are running silently in the background of your life every single day. Let's take a look. Just look at this list. That new song Spotify just recommended? That's because its audio features cluster with songs you already love. That movie Netflix is pushing on you? It's using association rules. People who watch movie X also tended to watch movie Y. And your news feed? It's clustering similar articles together. It's absolutely everywhere.
Here's a really concrete one: fraud detection. Your bank's algorithm uses clustering to learn your typical spending pattern. It builds a little profile of your normal cluster. So when a charge for $5,000 suddenly pops up from a country you've never been to, it gets flagged instantly. Why? Because that transaction is a massive outlier. It just doesn't belong.
So what's the big takeaway here? I think the true magic, the real power of unsupervised learning, is its ability to act like a master detective. You can drop it into the messiest, most chaotic dataset imaginable, give it 0 clues, and it just starts to find the structure, the narrative, the hidden story buried deep inside.
And that leaves us with this really fascinating, kind of mind-blowing final thought. Right now, we use this technology to find fraud and recommend movies. But what happens when we point this incredible detective at things like genomics or climate data or astrophysics? What